Hello, welcome to module 16. In this module, we will discuss the concept of two random variables having the same distribution. So, we will talk about the equality in distribution of two random variables. So, suppose I have two random variables x and y. I will say that they have the same distribution, which we will write down as saying that x has the same distribution as y if they have the same distribution function. So, two random variables having the same distribution function are said to have the same distribution. Now, it is worth mentioning over here that if x has same distribution as y, this does not mean that x random variable is same as y. For example, let us look at two populations. One population is population of all students at IIT Kanpur. Let us look at another population, which is population of all students at IIT Bombay. And suppose x represents the height of a randomly selected student from IIT Kanpur and y represents the height of a randomly selected student from IIT Bombay. Now, it may happen that x and y have the same probability distribution, or in other words, they have the same distribution function. But if you pick up a student at random from IIT Kanpur, his height may not be the same as the height of a student selected at random from IIT Bombay. So, what it simply means is when we say that x and y have the same distribution, what it means is they have the same probability distribution or the same distribution function. Now, many times it may not be straightforward to find the distribution functions, so we need to develop some criteria through which we can check whether two random variables have the same distribution or not. So, this result is in that connection. It says suppose x and y are two random variables and suppose their probability mass function or probability density function are fx and fy respectively. Now, if the probability mass functions or the probability density functions are also the same for random variables x and y, then clearly x and y have the same distribution. Now, this proof is very simple. For example, in the case of absolutely continuous case, I know that the distribution function of x, fxx, is same as minus infinity to x, fxt dt. But I know that fxt is same as fyt. So, this would be same as minus infinity to x, fyt, which is nothing but fyx. So, this proves that if x and y have the same PDF, then they have the same distribution function, which in turn implies that x and y have the same distribution. Now, another result which is very useful, it says suppose there is a h greater than 0 such that the moment generating function of x is same as moment generating function of y in a neighborhood of 0, then x and y have the same distribution. So, to check whether x and y have the same distribution, what you can do is you can find the moment generating function of x, moment generating function of y, and check whether the two moment generating functions coincide in a neighborhood of 0 or not. If that happens, you can easily conclude that x and y have the same distribution. I will not prove this result over here, but this follows from the uniqueness of MGFs, because we know that MGFs are unique. MGF of a function is unique. If there are two functions such that their MGFs coincide in an interval around 0, then the two functions are same. So, that would prove here that the two probability mass function or the two probability density function are same, which would in turn imply that x and y have the same distribution. Then the third result, which says if x and y have a same distribution, this would imply that hx has same distribution as hy for any function h. Now, this is very easy to prove. For example, if you call y1 as let us say hx and y2 as let us say hy, let us look at fy1y, which is same as probability that hx is less than or equal to y. Now, in the discrete case, this is same as collection over all those x belonging to Sx such that hx is less than or equal to y, fxx. But fxx is same as fyx, so you can write down this is same as fyx, which is nothing but fy2. So, if x and y have same distribution, then any function of h, any function of x has the same distribution as the corresponding function of y. Now if this happens, then we know that if x and y have a same distribution, so that means they have a same probability distribution function or the same probability mass function, so their expectations would also be same. And that is what the next result says. If x and y have the same distribution, then expectation of hx would be same as expected value of hy for any function h. Now this just follows from here, because this part C implies that they will have a same distribution. If they have a same distribution, they have a same PDF or PMF or the distribution function, so that is why the expected value has to be same. Let us go to the next slide. Let us consider a random variable yp. So I am considering a family of random variables yp, where p is varying over 0, 1. We have a random variable having this probability mass function. Fyp is n choose y, p to power y, 1 minus p to power n minus y. If y is 0, 1, 2 up to n, and this is 0 otherwise. It is easy to check this is a probability mass function. In fact, if you recall your +2, this is called the binomial distribution. Now here n is a fixed positive integer. So what I have to do is I have to find the MGF of yp and show that n minus yp has same distribution as y of 1 minus p. So what I will do is I will first find the MGF, and then I will show that MGF of n minus yp is same as MGF of y of 1 minus p. So let us try to see that. So mypt, so movement generating function of yp at point t is same as expected value of e to power t yp. So that means since it is a discrete random variable, I have to sum this quantity along with probability mass function over support. Support is 0 to n, so y is equal to 0 to n. E to power ty, which comes over here. Then the probability mass function, which is this, n choose y, p to power y, 1 minus p to power n minus y. So this is the movement generating function. I try to simplify the term. N choose y comes over here. E to power ty and p to power y I combine, which becomes pe to power t whole power y. 1 minus p to power n minus y comes as it is. Now if we try to see this quantity, this is n choose x, this quantity to power y, 1 minus p to power n minus y. So this is an expansion of 1 minus p plus p e t to power n. So this is a binomial expansion of 1 minus p plus p e t to power n. So I have been able to find the movement generating function of yp. Now using this MGF, I will try to find the movement generating function of n minus yp. So just to recall things from the last slide, let me write down what was mypt. This is 1 minus p plus p e t to power n. Now this p can be anything, because for different v I get different random variables. Now this is movement generating function exists for any t belonging to R. So it exists in a neighborhood of 0. So I define zp as n minus yp. So my claim is zp has same distribution as y1 minus p. Now to show this, I will show that the two have the same movement generating function. So let us look at mzpt, which is expected value of e to power t zp, which is zp is nothing but n minus yp. So this becomes e to power nt into e to power minus t yp. So e to power nt being a constant comes outside into expected value of e to power minus t yp. But what is this quantity? This is MGF of yp at point t. So this is same as MGF of yp at point minus t. So this is MGF of yp at point minus t. So that is what I have written down over here. But mypt we have calculated. So myp minus t would be same thing as this, except that t gets replaced by minus t. So it would be 1 minus p plus p e to power minus t to power n, e to power nt is outside. Now there is a e to power nt outside and power n over here, so I take e to power t inside. So that becomes p e to power minus t into e to power t, that becomes p plus 1 minus p into e to power t whole to power n. Let us try to compare this movement generating function with this. What is happening? Here the two are same, except that 1 minus p gets replaced by p over here. So 1 minus p gets replaced by p over here, or p gets replaced by 1 minus p. So that means this is nothing but moment generating function of y1 minus pt, because from here if you look at m y1 minus pt, what I have to do is I have to replace p by 1 minus p. So that becomes p plus 1 minus p et to power n, which is same as this. So this becomes m y1 minus pt. So that means the two moment generating function match on the whole real line. So they exist, they match in a neighborhood of 0. So by a result which we did just now, ZP has same distribution as y1 minus p. So you can see many times this moment generating function turns out to be very handy in verifying whether two random variables have the same distribution or not. Now let us talk about symmetric distributions. So a random variable x is said to have symmetric distribution about a point mu if x minus mu has the same distribution as mu minus x. So if such a thing happens, I say that distribution of x is symmetric about mu. Let us look at the last example. Last example what we saw is n minus yp has same distribution as y of 1 minus p. So I take p is equal to half. So you get n minus y half has the same distribution as y of half. Now you know that if x has the same distribution as y, this implies that hx has same distribution as h of y. So what I do is I take h of t to be t minus n by 2. So then this minus n by 2, which is nothing but n by 2 minus y half, would have a same distribution as this minus n by 2, which is nothing but y half minus n by 2. So what you get is, in the last example, you conclude that n by 2 minus y half has the same distribution as y half minus n by 2, which is equivalent to saying that the distribution of y half is symmetric about n by 2. Now if they have a same distribution, certainly they will have a same mean, provided the mean exists. So if mean exists, this would be same as this. Now the mean would always exist because y has a finite support. So you will be summing only finite number of terms when you take the mean. So the mean always exists. So this always holds. So if you simplify this, taking x spectral y to power half one side, you get x spectral y to power half is n by 2, not n by 2. So this would be n by 2.